Good evening, everyone. Myself, Suresh Kanoja. I am in Geosciences department. I am working there since last 10 years, and I started working on GRACE data for geodynamics and groundwater study. And later on, I started working on ground-based investigation also. So my field of specialization is GNSS, geodynamics, geophysical prospecting, so specifically resistivity, seismic, and ground penetrating radar, for to understand the crustal dynamics and to characterize the active fault and various geological hazards in the Himalayan region. So in this today lecture, I will be talking about the space and ground-based observation for crustal deformation studies. So as you know, this is very important field to understand, because it involves a huge risk to the this society when there is a great earthquake, major thrust earthquake. So we need to understand the active fault as well as the characterization of the seismic hazard, that how much the area is potential for the future seismic hazard, because till now the technology is available. With this only we can characterize the seismic hazard, and but we cannot forecast or predict, as we don't know that when this going to occur, because we have very limited information due to lack of this technology, and that's why we have sufficient resource to understand that how much area is seismically potential, where is the seismic gap, and where likelihood this future earthquake will take place. So this is giving a great help. The present technology give a great help for to understand all this information, to gather all this information, and this active fault characterization becomes very essential, because we know when there will be a great earthquake, then it can reactivate all those active fault available nearby this great earthquake. So that's why, and if the populations are big in those area, so it can give a very huge impact to the society. So that's why we have my today's lecture will be focused on how we can efficiently use this space and ground based technique for this crustal deformation study. So in this you can see some arrow. So this arrow is nothing but it's a velocity vector, and velocity vector of the site in the different region on different plates. So here you can see that how our plates all around the earth moving in different directions. So you can see that your this is our India. So, and these are the plate boundary, these are the plate boundaries. So you can see this big arrow means velocity is very high, and small arrow means velocity is less, and this is the resultant velocity actually with respect to the center of the earth. And we have used this ITRF, International Terrestrial Reference Frame, to get this absolute velocity of the site throughout the Indian region, throughout the earth. So here you can see that movement of the plate is not means equilibrium, or it is not same in all the plates. Also the direction is different, because you know this there are three processes: convection, conduction, and conduction. So this radiation and conduction actually works differently, but this convection current, which is occurring, this phenomena occurring in the subsurface, mainly in the mantle region, and your this fluid migration is taking place, and this thermal energy you're getting transferred through the movement, our motion, and from high potential to low potential, and because of that this movement is occurring. And you can see the dynamic nature of the this convection current, that how much dynamic it is. So because of that your plate movement is not same, and also it is going different direction. Then so that's why it becomes very important So this way it gives a very crucial information that how your different region moving with respect to center of the earth. Then you, with the help of this velocity, you can fix either with respect to India, either with respect to Eurasian plate. Then you to understand that where the crustal deformation is more, where the crustal deformation is less, and if it is high, so what is the means strain rate, our your compression rate, our convergence rate. All this we can quantify with the help of GNSS, our GPS data. And now seismic is SAR is also emerged. So I will not going into detail because I just have started working on SAR data also to understand the crustal deformation. So in near future I will be showing all those results once we will gather this good confidence level with the help of SAR data as well. So here you can see these GNSS satellites: Galileo, GLONASS, QZSS, IRNSS, GPS, Compass. So these all are operational all around the Earth. So in this all these constellations, this Galileo, GLONASS, Beidou, and GPS are global, and QZSS and IRNSS is regional. So they are giving the regional navigation information around the Earth. So GPS is oldest, and I think INSS and QZNSS is youngest, and this currently I am using GPS data to understand the crustal deformation in the Himalayan region. So these are some thermal imaging satellites, and you know as when we are working in crustal deformation, our geodynamics, so it's become essential to demarcate to work on anomaly also, earthquake precursor anomaly, which is generating due to the seismogenic activity. So as we know that just before the mega thrust, our great earthquake, the rock get overstressed because this strain accumulation limit is exceeding. So once this strain accumulation limit exceed, it get dominated on the coefficient of friction, and your rupture take place, means slipping take place on that plane, and earthquake occur. So before the occurrences of this great earthquake, it releases many anomalies, earthquake precursor anomaly. So there are so many techniques to measure these anomalies. So there are your thermal imaging, there are radon gases, there are total electron content, resistivity, electromagnetic. So many changes take place just before the earthquake, occurrences of the earthquake. So that's why these data sets become very crucial to use, so that some extent we should get the early warning of the earthquake. But as the earthquake occurrences nature, our dynamic, it is having very dynamic nature, so it always not give the same precursor in the same location. So as because of this dynamicity, so that's why we need expertise to get the confidence whether this is due to the earthquake or due to something else. And this is some microwave satellite SAR mission. So and out of this whole mission, the Sentinel one is open source. So where because this is very costly data. So but the Sentinel, which is your C-band, you can use this data to understand characterize the crustal deformation in the study area. So here you can see Sentinel is C, IIRS is L band, Cosmo is X band, Radarsat 2 is C band, TerraSAR is X band. So you can L band is very good actually, but due to this limitation of the budget, we and this Sentinel one we can use it. And if we are getting something very serious anomaly, so then we can go for this LOS pulsar, so that we can go little bit deeper, and we should get the confidence level of the future earthquake. So once you process this data, you have to model it. So there are so many modeling technique, like there are Okada Green function, then there are your posterior probability distribution function is there. So you can use all this model, which is based on your elastic half space. And once you put this data on those model, so then as this is observed information, so model basically it simulate and try to converge on your observed data, and then once it get convergence, and you get the best information about the your length of the fault, width of the fault, sleep, your depth, and log zone, log width. All this information we get once we model this data, GPS as well as SAR data. So these are some mission launched by ISRO, optical mission as well as your SAR mission, to understand the this surface nature of the Indian territory as well as other region. So you can use it, because we cannot only depend, we should not only depend on this SAR or GPS, also we should depend, because there are so many changes, geological changes on the surface, geological changes like geomorphological changes, geomorphic and indices changes, and then means maybe active fault, we can observe some this sharp changes on the offset, and this data help a lot to understand the paleoseismology, because paleoseismology is very crucial to understand in the region for the occurrences of the future earthquake. If we have a lack in the paleoseismic, then we cannot complete our work in the seismic hazard. So that's why we have to have this paleoseismic information of the region, which is which gives a very crucial information about the past earthquake, because with the help of this you can put the reference, and then you can give the information about the future earthquake. So these are some missions launched by ISRO, and this is our navigation satellite mission launched by ISRO. So we have total 7 satellites, and 3 is your geostationary, and 4 is geosynchronous. So that we should get at least minimum 4 satellite on our this antenna, and so that we can continuously track our location, and we can do static, kinematic, rapid static. So all this measurement we can do, and we can this can help in the disaster management system. So if we see, if we go into the history, so there were this traditional way to do the crustal deformation with the help of geodetic technique, because this GPS, your grace, these are geodetic techniques. So past techniques was to detect the motion of the geodetic movement with the help of triangulation method, which measures the angle between the monument using the theodolite, our trilateration, and measure the distances with the laser. So this is the traditional method, but this is very time consuming method. So presently, and there are VLBI, very long baseline interferometry, satellite laser engine is there, but these two are very costly affair. So it involve very huge money and all. So that's why it bring a limitations in our study. So then this GPS, after the operationalization of the GPS, which has been done in 1992, since then it bring a revolution in the geodynamics study, and which is giving a very crucial information about the movement and other phenomena to understand the mechanism, processes. It helps a lot. So with the help of geodesy, we can use is it for tectonic as well as earthquake study. So geodesy is the science of the earth shape, and find precise position. With the help of this, we can find the precise position, means millimeter accuracy, we can bring it, and then monitor the changes due to the tectonic process. And these are the process which we can estimate, model, to bring the information to the society, like plate motion, plate boundary deformation, intraplate deformation, earthquake cycle, volcanic processes, land subsidence. So I will touch some of the portions in this major objective, tectonic process. So as this NISAR is going to launch early in the next year, so this will bring another revolution to the geodynamic society as well as to the disaster management, because this mission involves this two band microwave signal, L band and S band, and L band frequency is 24, wavelength is 24 centimeter, and S band wavelength is 12 centimeter. So this two will give very crucial information about the mechanism and subsurface phenomena which is implicating on the surface. So these are the some microwave this range. You can see L band, S band, and C band and X band. So L band is here low frequency, and more wavelength, and X band is high frequency, our low wavelength, 3 centimeter. So here is the spectrum range, and you can see the infrared spectrum, and this is the visible. Means most of the optical satellites work on visible, near wave infrared, our short wave infrared, and this is very high frequency. So very few satellites none of the satellites work in this X-ray this thing. Few satellites work on ultraviolet range, but most of the satellites works basically starting from ultraviolet to microwave range, and this radio wave you will find mainly with the ground instrumentation, because microwave range satellite is not possible because we could, due to the limitation of the antenna size. So this will be the science. This will be the future science by the NISAR mission. So it will be giving this heterogeneous information about the this surface phenomena, like volcanism, like the glacier movement, your this drought, crop information. So all this and crustal deformations. So this will be, we will be getting this information. So this is the your satellite constellation configuration specification. So you can see GPS is having 24 satellites, plus your 6 is spare, is in spare. GLONASS is having your 28, so 24 operational and 2 in testing and 2 in maintenance. Beidou is having almost 50, and Galileo is having 24. Navik is nothing but it's the IIRS only, and it is given by our Prime Minister, Honorable Prime Minister. So it is having 7 operational. Then QZSS, Quasi Zenith Satellite System, is having 4 operational, 3 in QZO and 1 in GEO. So now I will come to the application. So here you can see that some of this part of the earth is witnessing your magnitude in the past earthquake. So you can see if you see the past earthquake, instrumental as well as non-instrumental this period. So we can see that here there was a great earthquake, like it was around 7 to 8. Then this is also 7 to 8, and we very well know about this 7.8 this Gorkha earthquake. Then very few earthquake we can see which is going 9. So there is one earthquake where it has gone around 9, but we can see the most of this land mass has witnessed this earthquake in this range 7 to 8, and where you can see the populations. So these are the populations in the India. So due to this Indo-Gangetic plain, and as food and resources, everything best here, so that's why we can see very big population in this region than the other region. So, and in this third, you can see that where the strain accumulation is going on along the plate boundary, as well as the other part of the Indian mass. So you can see it is mainly concentrated in the plate boundary deformations, where the Indian plate is converging to the Eurasian plate. So here Indian plate is subducting since last 50 million years ago, and it is continuously going beneath the Eurasian plate, and continuous crustal deformation is going on. So this region becomes very primary in the sense to understand the geodynamics, because this region can witness a great earthquake in near future. So as this your interplate deformation is also there in many region of the India. So like in your Gujarat region, Latur, So there was a medium earthquake or great earthquake, like a Bhuj earthquake occurred in 2001. So we should not forget, and we should keep this experience, because this zone are very very essential to the society who are living in this region, so that they should always be careful when there will be any earthquake. So they should show the awareness and always take the action. So how this your SAR mission is helping in the geodynamics. So this is the complete process you can see. So as SAR, you can see this SAR, it is giving the most of the people so far used during the co-seismic only. But nowadays this field SAR has been emerged for this interseismic study also, because it gives very crucial information about the line of sight velocity. So this line of sight velocity we can decompose, and we can decompose into north component, north south component, east west component, and vertical component. So once we decompose, so we can have an idea that how this and where vertical velocity is more accurate in SAR than the horizontal velocity. So we can use this information along with the GPS to characterize the region for the future seismic hazard. So here you can see that after the modeling, here the sleep at depth is modeled for this co-seismic activity where the fault has been taken place. So this is how you can do this modeling, and you can see the segmentation and the geometry also, fault segmentation and growth of the geological structure and topography. You can see that this is slightly uplifting, then fault propagation and folding is taking place. So then how this stress is taking place in the fault network. So all this you can do with the help of SAR data as well. Then with the help of this, you can demarcate this geomorphic indices. So for this you have to have very accurate this fore and after this optical data of high resolution, high spatial resolution. So once you have, you can get the ortho-rectified distal elevation model, and once you collect this data, you can do this geomorphic indices study, that how much area is active, and where and what is the nature, and what is the direction. So all this you can demarcate with the help of your distal elevation model data. So in this image you can see that the plate boundary. So this is basically 12,000 complete stretch is there. So this 12,000 stretch basically going to subducting toward north and continuous due to this moment strain accumulation is there, and you can see the extent of the strain accumulation. This is the extent of the strain accumulation which is continuously going on, and in the whole region, and where the future earthquake can be there. So this is some information, simulation information, when this subduction took place, Indian plate subduction took place. So you can see that 15 million year ago, around that you can see the arrow is going in inside the Eurasian plate, and this is going down because this is density of the Indian plate is more than the density of this Eurasian plate, and this is overriding on Indian plate, and this is subducting in the Eurasian plate. And here you can is the paleoseismic information. So you can see starting from this northwest to northeast, we have some knowledge, I would say some knowledge about the paleoseismic, and where there was a great earthquake and huge damage to this infrastructure as well as life was there. So these are the reference actually for when we are using this instrumental data for this present this characterization of the seismic hazard. So we should use as a reference, but we should not stop here for this paleoseismic study. We should keep doing this paleoseismic study, so that we should get more information of the past earthquake, and so that we can keep more reference when we are studying the seismic hazard. This is the geology and tectonics of the region. So you can see the main boundary fault and means MFT also, main fault thrust, and this is also called Himalayan fault thrust. And then you can see this is your Shiva IGP, and then you can see the Shivalik, then you can see the lesser Himalaya, higher Himalaya, then your Indus Sangpo Suchar zone. So you can see that. And also you can see the major thrust, but this is not the only thrust. There are so many active faults and neotectonic faults around the region, and which we have to characterize so that we can bring the complete knowledge to the society. And this is the vector, velocity vector, your with respect to the Eurasian plate. So why this is important? So, and what it is depicting? So it is depicting that your Eurasian plate having clockwise motion, and our Indian plate is having non-anti-clockwise motion. So this is bringing great information in the this crustal movement here. And you and also you can see that this velocity vector here in the means Indo-Gangetic plate is more, and it is continuously decreasing toward north in the Himalayan system. And why this is happening? Because here the velocity is getting decomposed. So that's why we can see the tremendous change and variation in the velocity starting from the IGP to the ITS jet. So because the velocity is getting decomposed. So and once you calculate the velocity, here the velocity is almost in IGP is almost 50 centimeter 50 millimeter per year, and in the your Badrinath region, Malari region, the velocity is almost 34 millimeter per year. So this is the resultant velocity with respect to ITRF. But if you fix the Indian plate and you apply the Euler pole of the Indian plate, then we have observed that this more velocity in the with higher Himalaya as well with respect to the your Shivalik, our and lesser Himalaya. So it gives the clear cut this information that more deformation is going on in the higher Himalaya than the lesser Himalaya, part of the lesser Himalaya and Shivalik region. So these are the zone where the megathrust earthquake can occur. So I will show you how we have modeled the data in the subsequent slide. And these are the vertical moment in the Himalayan region as well as in the your China region. So you can see the red is basically depicting the your subsidence, and blue is depicting the upliftment. So here you can see that due to the limited data, here we can see the some region is going down here, and here you can see part of lesser Himalaya and higher Himalaya is continuously is going up with the rate of something like 3 millimeter, 4 millimeter, 5 millimeter per year. So our eminent researcher, our scientist, has carried out the work here and to estimate the Euler pole. So you can see the Euler pole basically lying in UK and Europe region. So in by this present study, which is carried out by Jade et al. 2017, so it is occurring in this region. So an Euler pole is nothing but this is the pole with respect to Indian plate is moving in anti-clockwise direction. So these are the ITRF velocity you can see in all the Indian plate as well as in the Himalayan region. And this is the compression and extension. And once you have this precise velocity, so you can basically estimate the this compression and extension of this region. So you can see that the dynamic nature of the compression and extension, but as you can see this is less in this region, and you will get more in the higher Himalaya and part of lesser Himalaya. And this is the India fixed velocity. So you can see all these sites in the starting from this northeast Himalaya to northwest Himalaya concentrated in the southwest direction with different magnitude, and the maximum velocity is basically in the higher Himalaya, and minimum velocity in the Shivalik, our IGP is almost 0. And this is the your sleep rate basically in different fault segmentation. So you can see that the sleep rate is less in the Jammu area and maximum in the northeast Himalaya. Sorry, northeast Himalaya. And you can see Nepal also witnessing a high sleep rate, and where and it is there is a less recurrence interval, and big earthquake is occurring in short interval of time. And in the Uttarakhand region, the sleep rate is almost 17 to 18 millimeter per year, and this is mainly happening in the your Himalayan main Himalayan thrust, down deep of the main Himalayan thrust, because those regions are basically in ductile condition, and it is allowing the plate to move, and also the angle is little bit high than the up deep direction. So if you come to the up deep of the main Himalayan thrust, it is basically the brittle formation, and due to the brittleness, and also it is having less deep deep angle is less of the, so because it is taking more time to accumulate the strain energy, and coefficient of friction is more on the plane. So this is the information. So it is done by Bilham et al. 2019. So you can see the this how GNSS has helped to characterize this whole region, this seismic hazard, future seismic hazard. So you can see that there is a big seismic gap in this region. 1505, there was a earthquake in 2005, but rupture occur in very small patch, and energy has also not come to the surface. It in the sense that rupture should be there on the surface, but there was no rupture. So I would say that there is energy is not completely released, and energy has got stuck in the in the fracture zone, and due to that this will again witness a big earthquake in near future. So here in Uttarakhand we have witnessed these two earthquake, 6.8 and 6.7, 1991 and 1992, and this has released part of the energy accumulated in this Uttarakhand region, and you can see the interseismic stage. So here you can see this is this gives the information that the very big time, it took very big time to release the seismic energy, our strain elastic energy, and this is the co-seismic activity in 1803. Then again there you can see the interseismic stage, and then this 1991 and 1992 has released the part of the energy, and then again it has come into the interseismic stage only. So this has released very few very small quantity, and again it is very potential for this megathrust earthquake. So that's then we have to be very careful when we are living in this region, so that we can and how we can be careful. We have to bring the preparedness, we have to bring the awareness, we have to gather the knowledge, we have to spread the knowledge that how we have to react when the earthquake is there. So if it is maximize all this information, then we can reduce the life loss. So this is the global positioning complete this error information. So you have to do the orbit correction, clock correction, ionospheric correction, tropospheric correction, clocks, multipath, antenna phase intervariations, and apart from this your instrumental this correction, error correction, you have to have this modeling data also, like motion of the satellites, earth gravity field is there, so it is affecting the motion of the satellite, attraction of moon and sun, and then solar radiation pressure, then motion of the earth also bring this ambiguity in the data, like irregular rotation of the earth, lunisolar earth tides, then loading due to your atmosphere and oceans, and surface water and ice, and then propagation of the signal is also need to be modeled, like signal scattering, atmospheric delay, ionospheric effect, receiver noise. So once we do this complete once we apply all these models to the data, So we get the millimeter accuracy in our of our site, and which we use for this crustal deformation. So this is the some step of the GPS data processing. So there are so many softwares, open source softwares available for this geodynamics study, and like Gamut Group K is there, Gypsy is there, and Bernice is not open. It is you have to purchase. It is GUI based software. So this software is the this means standard software for this geodynamic study. So these are the some locations of this continuously operating reference stations. You can see how how does it look like. And this is antenna, there is a solar panel, there is a housing where your receiver is kept, and along with met sensor. And the work of the met sensor is to measure the pressure, temperature, humidity, so that if there is a we should correct this dry component, basically the temperature, pressure, and this humidity of in the data. Then these are the campaign stations. So this you can see the benchmarks. So this is your flag monument benchmark. This is a benchmark made by the Survey of India. So you can see all this benchmark. So this is Malari, this is your Mohand, this is Roorkee, this is Rajpur. So these are the some of the locations where we are continuously measuring the data for this geodynamics activity. And this is our study. So here you can see that the plate movement, the side movement here. So here the side movement is maximum, then it is continuously decreasing. And here you can see in the Malari region, the velocity you can see it is minimum with respect to your Saharanpur. So the region behind working in this region, so this there is a seismic gap in this region. So here we have attempted to understand the HFT MBT correct motion, as well as the MCT your motion like Vectorata thrust and your Munchiari thrust. So this is the data of derived from the campaign. So you can see all the sites and all the component is basically converging to the your R square is going to almost 1. So once you get R square nearby 1, so it means you have correct data, and this is this can be useful for this understanding the crustal deformation. And this is the your continuously operating reference station sites. Continuous data displacement you can see. So you can see the some gap also. So as this is mainly due to so many regions, maybe power issue, instrument is not working well. So that's why there is a gap in the data. Here also you can see the gap. So this is depicting basically if the displacement is going up, it means it is going in displacement mainly occurring in the north direction. And if the displacement is going down, means displacement is occurring in the south directions. So this is how we interpret. So you can see the displacement and this is having tectonic moment as well as non-tectonic moment. So once we remove this circular motion, means with the help of your moving average method, so means we are basically then we can get this non-tectonic component of from this continuously operating reference station. So this is the non-tectonic component. So this here we have detrended the data to, and after the detrending, the circular motion has been removed, and only the your non-tectonic component existence is there. So this helps actually that how this site is behaving in the influence of this your atmospheric pressure, your surface hydrological loading, and then your other phenomena which are non-tectonic in nature. So you can see the sinusoidal motion here, and this is displacement only. So you can see in the north component as well as in the east component in the Panthanagar region. And here in Mandal you can see very typical this sinusoidal motion. So as this region is very active tectonically, so that's why we see big amplitude of the sinusoidal motion in the Shamoli region than in the IGP, means Indo-Gangetic plane. And we can see this non-tectonic contribution mean maximum in the north component, and here you can see it is not maximum, it is minimum, so in the east component. So then this is the your strain rate of your this IGP and Shivalik region, and this is the your shear strain, and as well as this rotation, how the rotation is going in this region. So you can see that this IGP and Shivalik region has is witnessing this anti-clockwise motion, and also the strain shear is basically in the left lateral and right lateral strain rate, shear strain we can see. So it is also there, but it is having some it is less than your MCT region. So if you see here the shear left lateral and right lateral is a maximum than this Shivalik and IGP region, and this region witnessing the clockwise motion. So this brings a very crucial information that how this clockwise motion is going in this region, and here it is witnessing the anti-clockwise motion. And this your dilatation means volume change is more in this Vakrata thrust and Munsiari thrust region than in the HFT or MBT region. And this is the India fixed velocity. So here you can see the velocity vector almost toward the south directions, and here we can see the velocity in the southwest directions. So here the magnitude, you can see that it is not very high, it is almost 1 to 3 millimeter, and but here you can see the magnitude is high, it is like a 12, 13, 15, 16 millimeter. So so this gives a clear cut idea that this region is witnessing the active tectonic activity, and here the tectonic activity is less, means crustal deformation is less, as because this active plate movement is not there. So here it is continuously storing the strain energy. So if could be the, and also you can see the less seismicity in this region as compared to this particular belt, your 10 kilometer south and 10 kilometer north from the MCT. You can see the continuous seismicity is there, but you can see very few seismicity occurring in this region. So it gives the clear cut idea that there is a seismic gap, and here it is continuous strain energy accumulation is going on. And here this is basically Okada, this Teja formulation is there. So with the help of this Teja formulation, this strain rate has been estimated, and you can see that the pattern, the orientation, and this kinematic nature of this Indian plate and Himalayan system, that how the compression is going on, how the convergence is going on in this region. So this bright red, basically this is the high confidence significance, and this your faint color, faint red, and tint this thing red, basically giving the information about the medium this significance. But as you can see this here it is giving that more compression is going in this part of the Himalaya, and less compression is going in this part of the Himalaya. So this is the basically cross section of the Himalaya, and mainly starting from this your maybe HFT is here, then MBT is there, then the MCT is there, Almora Klippe is there, so Vakrata thrust, Munsiari thrust is there, all are overriding on your this Indian plate. So, and this is the MHT. So this is given by Julian, and it is published in 2009. So we have used this cross section to model our GPS data to bring this present seismic ongoing seismic activity in ongoing this crustal deformation in this area. So we have used this Okada green function, and this is the empty section. So this empty section is also helpful to understand your subsurface lithology, and this your fluid motion, your rheology, all this we can demarcate and characterize with the help of empty data. So as you can see, this is giving information up to 60 km depth. And here you can see this is the conductivity is more, and here you can see the conductivity is less, because this is here basically quaternary and shivalik region. So here you will get some saturation, but as this you have entered into the lesser Himalaya, and there are mainly metamorphic formation than igneous formation, means crystal formation, and those are very very high resistivity formation. So that's why you will get color like this. So, and also here surprisingly you can see in this zone the conductivity. So this is called mid crustal conductor, and these fluids basically, so you can see the most of the earthquake is occurring in this region, and there are mainly 2-3 regions occur due to of the occurrences of this earthquake here. One is region is this fluid, this flow of the fluid, and then another is the ramp of the main Himalayan thrust. So whatever the strain is accumulating, it is releasing in the form of small magnitude earthquake. But here, and also this fluid migration is taking from due to the potential difference, and it is also causing to earthquake to take place in this region. And this place is active, but this is a aseismic activity is going on, means there is no earthquake is occurring. You can clearly see there is a movement, but there is no earthquake occurrences. So this comes under the ductile condition. This is the down dip of the MHT, and this is the up dip of the MHT. So then you can see this your compression and the dilatation here. So you can see that this dark red is showing the extreme this dilatation condition, and this yellow is saying the minimum dilatation condition, means volume change is less here as compared to here. And you can see the model data. So you can see the observed and model data. So after this modeling, your locking depth is we have observed that locking depth is 17.5 kilometer, and it is nothing but it is in the nearby this region. And here the moment is almost in particular zone, this slip rate is 16.5 16.7 millimeter per year. And after adopting the deep stand degree, and we have used this chi-square uncertainty analysis to constrain the locking depth and the slip rate in this region. So this we can use this formula, we can use to estimate the seismic moment, and followed by the moment magnitude for this future seismic hazard. This is the co-seismic activity during the Nepal earthquake. So this gives a very crucial information that how GPS this displacement behave when there is a co-seismic activity. So you can see the offset in your north component, east component, and vertical component. So it has, and also you can see this in this region the area has gone down, CHLM station, but in this KKN4 you can see the area has gone up. So you can clearly see that here the displacement has gone up during this period, and here the displacement has gone down during this period. And in the third station also you can see it has gone up. So this this co-seismic deformation is very very crucial and essential, because once we have kept in the sampling interval 1 second, so we can some extent we may get the early information about the future earthquake. So GRACE satellite also is helpful, giving the information about the co-seismic activity, and but it is only possible when there is a big mass redistribution. If there is a big major mass redistribution is occurring due to the great earthquake, then GRACE mission also helpful in detecting all those changes around the earth. So I will not go in detail, I will directly come to the case study. So in this study we have done this how surface hydrological contribution is means contributing in and how it is modulating and perturbing the plate motion, in the Himalayan system. So you can see there here in the pre-monsoon, the mass load of the mass is less, and in the co-monsoon the load of the mass is more, and in the post-monsoon and the mass has been significantly reduced, but it is more than the pre-monsoon. So you can clearly see this anomaly, and which clearly gives an idea that this is having significant contribution to the crustal deformation, ongoing crustal deformation in the Himalayan tectonics. So these are the velocity, seasonal velocity. So you can see that the north component is more during the pre-monsoon as compared to the post-monsoon, and vertical also you can see that during the pre-monsoon it is going down, and in the post-monsoon it is going up. So this station basically established in the Chamoli region, and in Dehradun also we can see the similar contribution, but in the horizontal you can see it is not very high as compared to the Chamoli station. But if you see in Lucknow, Lhasa, then Hyderabad, ISC, so these are the stations where you can see very insignificant this changes in the pre and post. So which is very slight change we have observed in all these 4 stations as compared to this 2 station, and it is maximum in the Mandal station. So here you can see that this your correlation coefficient with your hydrological loading and your horizontal displacement, and means horizontal displacement means north south displacement and east west displacement. So we can see that the correlation is maximum, means it is going here almost -8, -0.8. So it's giving clear idea that this correlation coefficient is very high, means it is having maximum hydrological loading, producing maximum contribution to this station. And here Hyderabad ISC showing the minimum contribution, and Lhasa is also witnessing some contribution to this hydrological loading. So this is the interseismic stage of an earthquake cycle basically for this tectonic region. So you can see the red basically is the interseismic, and green is the coseismic, and blue is depicting the post-seismic relaxation. So this is the nature of this earthquake cycle. And and also one more interesting thing, here you can see it has taken less time to occur the earthquake. Here it has taken more time to occur the earthquake. So if it will take more time, so your this sleeping activity will be more. So you can see the sleep, how much strain has been released here, and due to this great earthquake, it having sufficient enough potential to trigger the another means medium hour big earthquake like this. So it can always possible. So we have already seen the Turkey earthquake, the Nepal earthquake, the great earthquake followed by the another big earthquake like 7.3, 7.2, like that. So as this is aftershock, but I would say that this is co-seismic activity only, and this post relaxation mainly occur when there is a plate movement. So it is now getting settled, so it is trying to settle. So during the settlement, this post relaxation, during the post relaxation, this macro earthquake, medium size earthquake occurs, and then again it goes under the interseismic stage. So here one interesting this step is there of this deformation pre-seismic. So this pre-seismic is nothing but it's the time where the precursors will take place. So these precursors, as I already talked about the precursors, so this I will show this case study that how this take is contributing in this earthquake precursor due to the seismogenic activity. So we have attempted this Mirpur earthquake. So you can see the earthquake of 6 magnitude occur here. So we have used these 4 stations to see the changes in the total electron content, which is mainly occur in the ionosphere. So the physics of this total electron means content for this earthquake activity is that just before this earthquake, not just before, means maybe 10 days, 15 days, 20 days of this earthquake, before occurrences of the earthquake, your this rock get overstressed and it releases the positive hole due to the pyroxy, your decomposition. So during this release, due to the high potential, this positive holes comes to the surface, and once it comes to the surface, again there is a potential difference to the earth's surface and the atmosphere. Then this positive holes goes into the ionosphere, and where it depletes the total electron content from the nearby region. And during the depletions, when the GPS signal is transmitting through the region, so it comes faster, little bit faster than the in the presence of the total electron content. So due to this difference, we are able to see the change in the total electron content. So, and also the stations which is very close to the epicenter, there this depletion will be more, and which is the station which is away from the epicenter, the depletion will be less. So here you can see at this time, in this region you can see the depletion, and this is Nurpur station. So you can see that here we have observed the maximum depletion, and it is continuously decreasing, and it is minimum in the Mussoorie region, which is situated here. And on the 17th also, so we have observed this anomaly in two time, one 10th September 2019, another on 17th September 2019. So here you can see very typical this change in the total electron content, starting from Nurpur to Jia to Ponta Sahib and Mussoorie, and this follow, and then on the 24th September 2019, there was a 6 magnitude earthquake. So that's why this precursors gives very crucial informations that there could be a seismic activity in within 20 days, 15 days, 1 month, like that. So that's why we have to continue, we have to measure this anomaly continuously, so that if there is a very big, if there is upcoming earthquake, so we can get some information about that, and we should immediately give this information to the disaster management. And we can get the possible epicenter also once we have good number of network around the region. So once we have this, so you can see the depletion of the this total electron content. So you can see here it is coming 36 kilometer from this reference point A, and this is having 28 kilometer. So you see 28 and 36, only 8 kilometer difference is there. So this 8 kilometer difference is nothing. We have got sufficient information about the upcoming earthquake. So this is giving a tremendous information. But the limitation is, if there is a solar activity, geomagnetic activity like this, and if it is this can bring hurdle, and this can bring limitations in this study. So that's why we have to be very careful. And when we are working on this anomaly, and we have to have very good knowledge whether it is due to the seismogenic activity or due to the your solar or geometric activity. And this is the GIM data, global ionospheric map data. So here you can see this has also recorded this negative anomaly. You can see here on 16th September 2019 for this this Mirpur earthquake. So as this earthquake was very catastrophic, so that's why you can see a very typical negative anomaly also detected in the GIM data. And this is the co-seismic displacement of this fracture developed in the Kenya region in 2000 18 time, and you can see clearly the offset in the north component. So the maximum movement took place mainly in the north-south direction, and you can see this cracks has move mainly in the south direction. So that's why the displacement has gone in the south direction, and east movement is less, and vertical movement is also less in these stations. This is another case study. So I have already discussed about the depletion of this total electron content from with respect to the epicenter. And this is the comparative study of your Nepal, and ongoing deformation in the Nepal area and in the Uttarakhand area. So you can see the plate in the Kathmandu region is still in the relaxation stage only, and continuous that's why we can see very big this compression rate in this region than this region and this region. So this region, we know that this is the seismic gap where the 1505 earthquake has been occurred, and it has stored sufficient energy, elastic energy, to bring the great earthquake in near future. And here also we can see the this compression is rate is more, as I told you that higher Himalaya has witnessing the more tectonic deformation than the other region. So here you can see the dilatation is more, and here we have you observed the very anomalous behavior in the this Shivalik part of Lesser Himalaya and IGP region, that here the we have dilatation is less actually, and means extension is going on. So that's why we have to adopt some more study, and we have to use the multiparametric data to give the explanation about the occurrences of this dilatation in this region. This is the modeling of the Uttarakhand region and the Nepal region. So you can see the model result and the this observed result, and this is the 3D model to put some information to give the information that the where the continuous earthquake is occurring, where is the locking depth, where is the sleep rate, where is the locking width, and what is the deep of the main Himalayan thrust. So for this Nepal earthquake, Nepal region and Uttarakhand region. And this is another case study for this seasonal hydrological loading. So here also you can see that this north direction is witnessing in the Nepal area more. So because the correlation coefficient is negative, correlation coefficient is maximum in the north component. If you see the this horizontal velocity, here the east component is witnessing less correlation due to the hydrological activity, and vertical component particularly in this region, and witnessing the maximum hydrological in this region. So we can use the seismic microgenation. We can conduct seismic microgenation with the help of your PGA analysis, means the seismic data, your multi-channel analysis of surface wave, and we can give information about the that how much area is this means how much amplification would be there, how much this amplification and this means damage will be more. All this we can give more information with the help of this MASW data. So you can see this Uttarakhand, this Dehradun region. After this analysis, this is the shear wave velocity, and this velocity has been derived with the help of this Rayleigh wave information. So you can clearly see that this rate basically has the maximum potential, where the maximum amplification can be there if there is a surface wave. So it's a shallow earthquake of 6 and above can means bring more disaster and more deformation in this rate patches. And if this there is a deep seated earthquake, so we know that for deep earthquake most of the this surface wave get dissipated, so few energy comes to the surface from this surface wave, and less damage occur. But if it is shallow, like 5 kilometer, 10 kilometer, 15 kilometer, so and this brings a sufficient this surface wave, and it cause maximum this damage to the your soil area, alluvium area, and less deformation in the hard rock area. Like this you can see part of this where there can be a less damage due to the presence of the hard rock. So these are some active fault in the region. You can see Biharigarh thrust, then your this SSF as there. So all this there, MBT is there. So we have to get this paleoseismic study. So we have to do the remote sensing, followed by the geophysical investigation, then trenching, then dating. So once we do this complete set, then we can gather the sufficient information about this paleoseismic activity occurred in this region, and we can keep this as a reference, and once we use the GPS data, so after this precise velocity, we can model, and we can gather the information about this future seismic potential in this region. So this is the one area, Kalam area, where the trenching has been carried out by the eminent scientist Dr. Philipson. So you can see there was a 3 generation of fault, means this region has witnessed 3 back to back this thrust activity, so mega thrust activity, and you can see the liquefaction is also there. So if there is a liquefaction injection, it means there was a very huge this earthquake has been huge energy has been released in this energy, because this is only possible with the when there is a megathrust earthquake. So we have performed this geophysical investigation like electrical resistivity tomography, seismic, MSW, and GPR ground penetrating radar to observe the and characterize these faults and the liquefaction injection in this region, to so that we can bring means we can get the sufficient information, and we can bring our confidence level high, so that when we are going to the other site, we can use this same instrumentation, same technology, and we can quantify all this fault and all. So you can see this quaternary formation. So as this is having alluvial, so that's why this is dry mainly, and water content is very less. So you can see the high resistivity, and this basically demarcating the Shivalik, this, and where there is a resistivity is low, and here you can see the water saturation is more. So, and also you can see the typical this change in the lethal resistivity contrast, and this resistivity contrast is nothing but due to the lithology change. So this is the tertiary formation, and this is the quaternary formation. So when we get such signature in the resistivity data, so it means this is giving there is some discontinuity. Now we have to confirm whether this is fault or something else. So then we have to have some multiparametric this data to get the information, and then followed by the trenching. So once we do the trenching, so we can say yes, this is the fault, and when this faulting has been occurred, and what is the current moment and all, we can demarcate with the help of all this data set. So here you can see the your shear wave velocity change, and your this basically it is dipping toward the your north, and you can see the shear wave velocity is increasing toward depth, and here it is maximum, and here it is minimum. So you can clearly see that this depicting the basically the fracture zone, that due to this two fault, and this typical velocity change we can see from this two formation, from the quaternary formation as well as from the tertiary formation. And in the GPR we can clearly see that here there is a offset in the reflector, as well as this bed is truncating, this reflector is truncating in some of the region, and also there is a hyperbola, small hyperbola is there. So this hyperbola is nothing but this is mainly due to the sand injection, so it become a mass, so it's a dry mass. So then when this GPR is passing from there, so as it is like a 3D body, so that's why we are getting the hyperbola. And wherever there is a means change in the this offset, change in the bed is there, so we are getting the offset in the reflectors. So this is the present study which we are attempting using the SAR data, and you can see this. So we are now we are now modeling this data with the help of this probability posterior probability distribution function to characterize the seismic hazard of this region. And we are here basically doing the joint inversion of seismic and SAR data. And here you can see the complete rupture of the Nepal Bihar earthquake. And here you can see the sand injection also, which took place due to the megathrust earthquake. So there are few earthquakes which has where the surface rupture is there, like your Jammu earthquake, and then your this Kangra earthquake is there, then your Nepal Bihar earthquake is there. So there are few earthquakes where there is a surface rupture. So if there is a surface rupture, means energy has been released, and now it will store the energy, and it will take more time to accumulate the energy so that future earthquake will take place. So that's all from my side. So from here you can see that how this multi-parametric approach help us to understand the crustal deformation and to characterize the future seismic hazard in the area. So thank you very much.